Good morning, everyone. Welcome to the GFI Alternative Protein Scientech Seminar, the APAC edition. So for today, in terms of organization, I'm gonna have a short announcement of some GFI activities, and then we're gonna go on to introduce our speaker today, Professor Chow, and then we will be doing a deep dive onto the topics of precision fermentation. But first thing first, in terms of the usage of the webinar, if you look at the bottom of your screen today, you can see that there's a Q&A button and there's a chat button. Please make sure that if you have any questions for our speaker to address, please keep it in the Q&A button. And we also include within the Q&A section that you can upvote any question that someone else is asking, so that you can get those questions up top and we can address them first. So before we dive into the seminar today, I would like to announce that GFI is collaborating with SIAW to set up a scientific symposium day during the Singapore Agritech Food Week. And the session itself is free to register, and you can register at the website of SIAW. So please make sure to check that out. We have a lineup of different experts and panelists regarding alternative proteins. So we'll be very excited and hope to see everyone's there. So with that out of the way, I would like to introduce our speaker today, Professor Yvonne Chow. Dr. Chow holds a degree in chemical engineering and a PhD in biotechnology from University of New South Wales. She has 25 years of experience in fermentation and bioprocess research. In A*STAR, she established the Biotrans, or the Biotransformation Innovation Platform, the Fermentation Platform, and the ICE Industrial Biotechnology Laboratory. She's currently lead the solid state fermentation team as SIFBI and A*STAR. So today she will share with us a bit more on the precision fermentation and how that's applied in alternative proteins. If that's ready, Dr. Chow, you can take away the stage.
Thank you very much. I'd like to show my appreciation for this opportunity from GFI to give a talk on precision fermentation. So my name is Yvonne Chow, and I'm at SIFBI. Okay, can you see the slides? So I'm working at A*STAR in Singapore, Agency for Science, Technology and Research. And this is a new institute that has been just set up a couple of years ago, the Singapore Institute of Food and Biotech Innovation, in short, SIFBI. What do? We have three major focus areas, all surrounding food, with the aim of developing novel, tasty, nutritious, and healthy food through different engineering approaches. So that includes food and ingredient innovation, as well as sustainable biomanufacturing. And that involves biotech as well. And in Singapore, because we are not self-sufficient in food source, so we are very much into driving for the economic health and food security areas. And our institute, our capabilities span across nutrition, discovery, shared analytics, biotransformation, strain engineering, and food process engineering. So let's get into the talk today. As an introduction, maybe not necessary for some of you, what is biotechnology? It is actually simply technological application that uses biosystems such as living organisms or enzymes to make useful products. And this can have a wide-ranging application areas, from chemicals to food to pharmaceuticals and agricultural industries. The workhorses here are any microbe, including yeast, bacteria, fungi, microalgae, and they can be the wild type or the genetically modified strains. In fact, it has been used for a long time in history to produce fermented foods. You're very familiar with beer, bread, cheese, and even cocoa and coffee. So what is precision fermentation? It is the breakdown of so fermentation is a breakdown of an organic substance, usually sugar, by a microbe, resulting in the production of one or more substances. So in that context, precision fermentation is then where we leverage on microbial cell factories to produce high value or functional food ingredients, for example, with high yields and purity. And it is seen as the next step in the evolution of fermentation, made possible by the advanced technology. At the cutting edge would be AI, but we also have genetic engineering, synthetic biology, systems biology, bioinformatics, etc., which are all supporting the progress in this area. So what we want to do when we're doing precision fermentation is to make specific customized molecules with a particular target that we desire. And this can be to, for example, to make food with certain consumer taste and feel or better performance. So essentially, we are saying that we want to go from this kind of equipment, hardware, and a factory where we were just producing beer. And as you know, beer comes in many different forms, depending on where it's made and, what's the time of day, etc. That's not going to be suitable for precision fermentation. So we need to get to something that is more industrial, standard, consistent to produce a high value ingredient. And we also often talk about the process being designed for quality. And we also are concerned with things like sustainability and life cycle assessment. So over at A*, we have a bioprocess platform for precision fermentation, and it looks something like this. This will be at the bench scale, where we do intense process research and development. So this will include taking a strain that has been designed by our strain engineering colleagues, and we will apply various strategies to understand how the bioprocess should be. So we have bioprocess engineering and optimization, process control, automation, inline monitoring, and coming with this, of course, for monitoring analytics, as well as at the end of the fermentation, product extraction. So the goals here are typically trying to maximize yield, titer, reproducibility, and productivity. And the process can be of various forms. So you can mix and match the different unit operations. So if we break down a bioprocess, what does it involve? In these days where we are aiming for sustainability and waste valorization is very important. So you could start with a waste stream, but that needs to be treated before it is ready for fermentation. And in that process, we could recover some useful ingredients through physical chemical recovery. And then that goes into the fermenter. After fermentation, then the separation starts. So separate the cells from the media first. And from here, you will also be generating waste stream. You could choose to put that into another bioreactor before it, to clean it up and get something that is more suitable as an effluent. And then the other stream, which is the desired, containing the desired target, would have to go through a series of extraction processes, purification, and finally, there will also be a waste stream at the end of it. Solvent is used frequently in downstream extraction, and that is also something that needs to be treated or recovered. So an example of a bioprocess would be like this. And there are so many things that we have to optimize or focus on and make sure that they are all satisfactory before we can go to the industrial process. So these, just to mention a few, are optimizing to maximize productivity, and very often we go for high cell concentration to increase the volumetric productivity. And of course, we want the target title concentration to be as high as possible. And after that, we want to minimize the downstream costs. So minimize the processing required and minimize the amount of waste and toxic byproducts being produced. That would also mean having to have a good selectivity and yield from the fermentation. So economics is the driving force in an industrial process. And of course, reliability and sustainability. So nowadays, we are talking about a lot of alternative protein fermentation. Just give me a sec, I'm seeing the top bar. Oops. Not sure. Okay, never mind. So alternative protein, or in other words, microbial protein, is now of focus in the world trends, because it is also another sustainable form of alternate protein. And this is a large focus of our research here. We are seeing an increasing annual investment into this sort of microbial protein and forecasted into the future. An example would be microalgae. It's a very good source of protein, and this has been an attractive option to several companies, because microalgae can offer a full nutritional profile, including all the amino acids, as well as beneficial health compounds such as the DHA, omega-3, and various vitamins. So if we compare that to growing cows feeding fed on grass, then of course this is a much more sustainable option in terms of the land use. So the way we see it for bioprocess development, the stages are basically run the fermentation, and the experimental data can be put into a kinetic model, and then you optimize it. And after optimization, that will give you an idea what and how you need to control. In this, to facilitate this, inline monitoring is important, and later on process control and optimization. There's a lot of math and computational techniques that go into it, from modeling to optimization, which I will go into in my talk. And then sensitivity analysis will be done. And all these will be used for the process control. And finally, we want to scale up the process. When we scale up, we need to take care of non-idealities. Also, we should consider the state of the cell, so the cell physiology, population dynamics, and the metabolic flux. Generally, there are three ways of approaching optimization. For an approach which does not require a background in bioprocess engineering or any science, we can just use statistics. That's the design of experiment. And if for experienced fermentation engineers, we would be able to use the kinetic model based on bioprocess engineering equations. And what is quite popular as well coming up is using bioinformatics, going down to the cellular level to look at metabolic flux models. So this is the first piece of research that I'm going to share, and this is focusing on how we used modeling to understand a microalgal system which was producing glycerol. So this is the Dunaliella tertulecta microalgae strain, and it's very unique that it is able to produce glycerol because it uses glycerol to combat osmotic pressure in high saline environments. This is a photosynthetic process. So the substrate is carbon dioxide. So we wanted to see how carbon dioxide is converted into the products, including glycerol. So first of all, if we look at the growth curve, we can see that there's growth at first, but only for 2 days. And after that, you get self-shading of the cells. So that's meaning there is light coming in, but only the cells facing the light would have access to the light, but the cells beneath are being shaded. And this becomes more and more serious as cell concentration increases. So this is, we found there is an exponential attenuation relationship. And because glycerol is being produced by two possible routes in the cell, so that's first of all, fixation of carbon dioxide, and the other is conversion of a reserve starch pool within the cell. So we looked at what was accumulating in the cell, and it's very interesting that we see the intracellular glycerol remained constant while it is carrying on photosynthesis. The starch only increased quickly at the end when it was reaching stationary growth stage. So what's happening with the glycerol? It's actually being excreted into extracellular glycerol. And when we measured that extracellular glycerol, we took the values and fit a model to it. And the overall carbon fixation rate was constant, and it fully matched a mass balance where we could assign the intracellular components and the extracellular glycerol. So this is how we characterize the system. Okay, moving on to the statistical method of design of experiment. There are, unlimited things that you can look at. However, success is never guaranteed. So we try to focus on input factors and select what are the factors that we wish to vary based on maybe experienced guess on what are factors that are going to be affecting our process. And then we measure the output responses, such as biomass and product, yield or rate. And these values are collected based on certain experiments laid out by the design of experiment technique. The first round of experiments will give you what are the significant factors that should be focused on. And then another round of DOE would then tell you what are the conditions, the optimal conditions. Of course, these have to be validated by experiment. So you can get a response surface plot showing what are the trends as well. So we went and used this kind of technique to optimize still the same microalgae producing glycerol, but this time trying to look at how we can optimize the process aiming at the media. In microalgae, it's obvious that it will need carbon dioxide, and nitrogen and phosphate are macronutrients that they need. But many people, it's not so often that people would focus on the micronutrients. So we were curious whether the micronutrients which we are adding in as stock solutions, how important they were. So these 5 groups of micronutrients are studied, and a linear regression showed the main effects and interactions between these different groups. Some were found to have an insignificant effect on production and growth. However, others demonstrated antagonistic interactions. So that was interesting. So the gist of the whole exercise was that we went through, find the significant factors, and also, what are the how to optimize based on the media levels. So if you see, we have 5 stock solutions, and the results showed us that the best, for example, best cell concentration can be gotten by having all the high levels of micronutrients except group D that should be omitted, that's containing zinc, cobalt, and copper. So that was where it has some inhibitory or antagonistic effects, interaction with the other groups. And conversely, if we do the opposite, that would be giving us the least or the worst cell concentration. And similarly, we can do that exercise for the glycerol production. So this set of data, and referring to the conventional mixture of media down here, this told us that for good cell growth, we don't have to have group D, because you can see we have similar cell concentration. And for good extracellular glycerol production, you would omit group B and group E. Again, you still produce or even slightly higher glycerol. The interesting thing is, if you were to use the wrong concentrations of micronutrients, the difference between the best and worst case scenarios is quite large. And that really shows the importance, the significant effects of the micronutrient composition. One of the strongest effect was seen in group C, which is manganese and boron. So we looked further into that, and true enough, as you increase manganese, you see a significant difference in the amount of cell growth and extracellular glycerol that's produced. Why is that so? Because manganese is associated with cellular SOD superoxidase dismutase enzyme, and that's the first line of the defense against damaging effects of reactive oxygen species during photosynthesis. So with the light and respiration, the cell needs to combat the ROS. And with manganese, it was able to produce higher amounts of SOD, and therefore become more robust and produce higher yields. Okay, so that's nice. We could do that with microalgae. But just a note, with something like fungal systems, it's a different story. It's more messy, and reproducibility is not really there for many cases. Difficult to collect data as well because of longer culture cycles. So in such cases, we would probably not go for a DOE approach, but other science-based rational experimental designs. The next area that I will showcase is E. coli. So in SIFBI, we have an E. coli platform that's set up to produce a whole host of compounds, from carotenoids to apocarotenoids and terpenoids. And we have the task of building an optimized bioprocess for this E. coli strains. There are lots of parameters that can be optimized or need to be optimized, and not just what we are putting in as a nutrients, what state, what physiological condition do you want the cells to be in, and after that, when you do fed batch, what is the feeding rate, and also the inducer is added to start production of the target product. When should that be, and how much should be added in, and that all needs to be optimized on top of the bioreactor conditions. So actually, you'll be surprised how many people simply do trial and error. That, of course, does not guarantee an optimum. Statistical design would require a lot of experimentation as well, but it does not use scientific input. So what we are trying here is using a model to guide optimization, because there are some equations from the kinetic models and so on. So let's we thought, let's give a try. This is how the cell sees a fermenter. Its environment includes all the oxygen, pH, and temperature levels, stress factors, and a whole host of products are being produced from the substrates that is taking in. And in that process, there are different states that we can study, so energy, respiratory quotient, and cell oxygen uptake, viability, etc. So we're trying to take this whole complicated system and build around it online monitoring and control. As expected, because it's very complex, it's not so easy to characterize and model. So a lot of people are then looking further into the cell to understand and characterize based on the DNA and the protein production. So what we are focusing on, let's go from the high level first. The E. coli, under aerobic conditions, is producing, it has an oxidative process and produces biomass. Not so much of the overflow, but overflow then increases when you have limited oxygen, and that process produces acetic acid. There's also the mixed acid pathway that produces various acids. And different approaches can be used to model a cell. We are going first for the simple one, unstructured and unsegregated. There are other approaches where you can consider all the non-uniformity across the cell and across the locations. So incorporating systems biology, we would like to optimize the bioreactor conditions through looking at what is the system, what's the flux, and looking at perhaps metabolomics, and through perturbation, understand more about the process and predict what's going to happen. There are two levels that we can derive our strategies, which is genetic models, as mentioned before, and genome scale models. So genome scale models are where rather than just predicting phenotypic characteristics based on main central pathways, the entire metabolic network is reconstructed as a matrix. So a little bit about that, also called flux balance analysis. It's a framework that analyzes all the metabolic networks using a genome scale model. And as you can imagine, you need to have a very well understood strain in order to do this. So E. coli is one of those. So this would then be optimized and to satisfy, for example, maximization of growth rate. However, FBA assumes steady state. That means it's not a dynamic, cannot be a dynamic system, and no accumulation occurs in the cells over time. This, of course, is not compatible with dynamic bioprocess. And there's also dynamic flux balance analysis coming in to try and tackle that. And that extension of FBA is where FBA is repeatedly solved with respect to time. And this metabolic flux is reprogrammed depending on the dynamic conditions inside the bioreactor. So in other words, the steady state genome scale model is coupled with differential equations that govern the change in the bioreactor variables. So this becomes quite a huge computational problem, which comes with it into computational issues. So we attempted to take some literature, metabolomic data, and figured out how we can do something of our approach, which was a non-structured, non-segregated, incorporating important pathways and regulations for aiming at the 5 variables: biomass, glucose, acetate, dissolved oxygen, and the product. Our model looks something like this, and on the right, you can see the fit of our model with the data that was from literature. So okay, that looks good, and we went and tried this in the lab. And so this is one of the example of data that we have where we were doing a fed batch process feeding glucose on in the profile you see on the left. And this glucose feed rate is semi-optimized using the model as a basis. And then we fit that model. So this is just a snapshot, of course, doing this whole exercise of model building that can be used for process optimization requires valid fitting and then testing, validation, and then predicting. Okay, E. coli is nice, very simple. Let's go on to fungal culture, the other story. Forget about modeling for now. The bioreactor is something that we have been focusing on because fungal is a suspension system where you have mycelia, and these fungal mycelia can clump, and that causes a big issue. So you are dealing with clumping and suspension mixing, and hence poor reproducibility and very often failed bioreactor processes. We have designed a microfluidized bed bioreactor with the aim of offering good mixing and mass transfer. And we focused our research on the fluidization quality. This kind of fluidized bed reactor has been used in the chemical area for several decades, for example, for pyrolysis. And first question will be what flow rate to use. So essentially a fluidized bed is something like you see on the top right, where you have a riser, and that's where your reaction or bioreaction is happening. Because it's in the inlet, you have say liquid going in, so it will then fluidize the solid particles upwards, and any overflow will then be settled in the settler and returned back. And the flow rate to use will depend on the minimum fluidization velocity, which brings a packed bed, such as what you see on the left, into a fluidized or loosened bed. And that can take different formats, some involving channeling and some being an expanded bed. The design will influence the kind of fluidization that we are able to achieve. So these on the right are examples of the sparger designs that can be used. And the gas flow is meant to completely support the bed weight. And radial mixing uniformity will depend on these sparger nozzle arrangements. We had a small microfluidized bioreactor made through 3D printing, and with a collaboration that we had with a PhD student. And we used that to characterize the flow. And you can see here that when you vary the gas velocity and the liquid velocity going in, you have very different results. So a mixture of gas and liquid, as you see on the third video here, is what we want to achieve. Okay, let's bring it to real life in the fungal system for this production of raspberry ketone. This is a commonly used ingredient for the food industry, for food and beverage for raspberry flavor, but the natural form is not economically available yet. We have this fungus over here that naturally produces raspberry ketone. However, downside is that the raspberry ketone also then gets further converted to the side product, raspberry alcohol. When we grow these so-called mushrooms in sunburst culture, you actually get pellets formed. So this is very typical of many fungus. So you can see this is what the flask culture would look like. Of course, this is unscalable. And if we put it into a standard stirred bioreactor, we will start to see shear effects, and the shape of the pellet will change, etc. We also tried a different kind of bioreactor, so panel bioreactor. This is commonly used in the photobioreactor design. It's airlift, so you have let's say 4 or 5 bubble columns going up. This didn't work well actually, because there were several dead zones at the corners, which will then soon start to form clumps. And when we put in a stirrer bar over here to stir things up, then as expected, everything will actually get smashed up. So you don't see the pellets as such. So our system from just now, we made a bigger version of the MFP. And in this case, you can see the pellet morphology can be maintained, and we get a nice distribution of the particle sizes with each stage of fermentation. And through this system, so we have something like this circulation up through a platform here, and then the fungal pellets are distributed upwards. We managed to achieve what's this? 70 milligrams per liter of raspberry ketone. Doesn't sound like much, but the maximum reported in literature before that was barely 10 milligrams per liter. So that's raspberry ketone. The last thing I'll talk about is scaling up. So basically, if you have a process that you have already developed and you're happy with it, then we would think of scaling up for the purpose of industrial production. You can see that different systems here at different scales are quite different in configuration and type of mixing. So scalability is definitely an important issue. So as mentioned, you will take the bench scale bioprocess design that has been optimized, and next step will be to adapt it to the process, adapt the process to the pilot scale conditions. So this is our pilot scale bioreactor in our lab, and try to implement that. If it doesn't work as we expected in the bench scale, then we can do some fine tuning to the conditions and settings. So that's pilot scale of about 200 liters. But then what happens if we go further upwards to large scale, industrial scale? So I don't have the full answer for how to go all the way to industrialization for you, because we are a research lab. But I can definitely describe to you what might happen in an industrial bioreactor. So one of the most severe issues is the oscillation or fluctuation because of the scale. So you have a mixer which is in large scale very often insufficient. So insufficient mixing will lead to time between entry of substrate and actually it reaching all the different locations in the bioreactor. Typically, you would have, for example, glucose feeding on the top and air being sponged in from the bottom. And the poor cells would see either very high glucose if they are sitting at the top with no air, not much air at the top, or at the bottom, if they are sitting down there, they would have lots of air, but they are going to be starved for glucose. So we wanted to understand whether how severe this fluctuating conditions is on E. coli. And this is what we tried to do, simulating a fluctuation of the air supply in our bench scale bioreactor. So this is manually switching the air off and on. And the results are here. So just by fluctuating the oxygen level in an E. coli bench scale bioreactor culture, we can see that there is already an observable difference in the growth trend. So imagine if we were to take our process from bench scale to industrial scale, it will not be able to get the cell yields that we thought we would. The growth rate is 20% lower, and the biomass achieved is lower, even though the glucose utilization looks almost the same. So that's what the cells are doing, is that the yield, the biomass yield has dropped. And if you notice, the acetic acid has also increased significantly. So these are all indicative that the process is no longer as efficient in producing biomass, because the cells are in a state of suffering due to these fluctuating conditions. So one can go more in depth into understanding what's happening in the cells under such conditions. So these factors affecting heterogeneity in the bioreactor can actually bring about changes in the overflow metabolism and cause stress responses and affect cell viability, ultimately affecting the overall product yield and productivity. We are studying these effects in our laboratory with our downscale system. So the advantage of this is being able to just use a 15-liter scale bioreactor, play around with it to study how fluctuating conditions can affect cells in a culture. And that is basically what I have to share today. I would like to express thanks for many people who have collaborated and supported and helped with all the research here. I'm sure I've missed out several. It's non-exhaustive. We have been working on the E. coli with NUS, and the respiratory ketone project was with University of Newcastle. Thank you very much.
Thank you so much, Professor Chow. That was very intense. We have one raised hand participant. Can you, Anaman, can you leave the question in the Q&A box so we can address your question? While we're waiting on that, we actually have one big question already coming in. So, hi, Dr. Chow, thank you for your talk. I've got a few questions. What are the major challenges in scaling up precision fermentation?
What are the challenges preventing scaling up?
Yeah.
Okay. If I start from the beginning, the equipment. So a large-scale fermenter is definitely a heavy investment, a lot of capital that needs to go in. And because of that, there are not that many opportunities to actually test out a process before actually going to the industrial application. And there's no simple formula, although there's some successes, but there's no simple formula to just scale up, say from 5 liter to 1,000 or 2,000 liters and beyond. So that's first of all the facilities, and the inherent problem would be the biosystem. It's not like a chemical system, it's more complex. So as we've seen, the heterogeneities aspect will already have a knock-on effect on all the different complex processes in the cell, and it's not so easy to predict what it's going to do. So it's like the difficulties in prediction, but you don't have the real-life equipment to try it out in.
Thank you. So the next question is on the design of the fermenter. In your experience, how does the design of a fermenter differ between different microbial systems and from that of a conventional bioreactor used for like mammalian cells?
Okay. The standard bioreactor on the market now, which is what we call submerged bioreactor, is pretty much all the same. And it has been so for several decades. And those are definitely fine for, or rather the best that we can design for liquid culture. So that would include microscopic cells bacteria, yeast, and microalgae. These are all very suitable for those standard bioreactors. Next, for mammalian cell bioreactors, although it's not my area of expertise, but I understand that it has unique requirements. And for example, mammalian cells may need to anchor on a solid surface. That would make the bioreactor very, very unsuitable. So there are strategies such as using microcarriers and such to provide that surface for cells to adhere to. And what I have shared today is the next stage in the spectrum of liquid to solid fermentation. That's a fungal suspension. So once you have fungal growth, then it will clump and clog. These are all very major issues that cause a bioreactor to fail. So the mixing and the configuration of a standard bioreactor may not necessarily be the most suitable. It can be used. We are doing that for some fungal fermentations. But it really depends on also what morphology is desirable for good production. So if you need to keep the fungus as pellet form, then something that is going to have a high shear in a standard bioreactor is not going to work. In other situations, it's so thick, the fungal culture gets so thick, the mixing is very difficult with a standard bioreactor. So that's why we are looking into designing novel bioreactors for fungal fermentation. And if you go further down the line to what we are dealing with in food solid state fermentation, then it's a worse scenario. And we are also having to look for different designs for different fermentations.
Thank you. The next question is around waste product. What are the major waste products obtained in a typical precision fermentation process? Can they be repurposed and feed into other bioprocess?
And yes, indeed. Water actually is a precious resource which is generated in large quantities if we just do a simple batch bioprocess. So we need to look at how we can recycle water and any other media components. For example, if the nutrients are not fully used in a bioprocess, then that can be recycled. The other waste that is generated, well, for example, biomass itself can be a waste if it's not part of your target product. That's also an issue. Such waste or organic waste can be subjected to, for example, an anaerobic bioreactor, which is typically used for waste treatment. And that would produce, for example, biogas that can be used. One thing to note is that when we want to recycle the waste stream, it may contain some of the inhibitory byproducts generated by the cells themselves, and that can affect your bioprocess if you recycle it. Yeah, so that's out of a fermenter. That's typically the kind of waste that we will see.
Thank you. I think the next question is still around fungal fermentation. He asks whether do you custom design your airlift, or are there some standard fermenters that can be utilized?
There are standard airlift fermenters actually. I believe they could do the job. How well it does, you need to test it out. Yeah, we would always have to actually try it out to know for sure for your particular strain and fungal system how suitable it is. But airlift is a common configuration that's used where you're dealing with shear sensitive cells.
So this question is around whether you have attempted to work on multi-species microbial communities, something similar to typical food fermentation.
Sure. That part of my research was not included today. I was thinking whether we would call it precision fermentation. It's a very interesting problem. Food fermentation is where whatever drops in will just grow. So it's a consortia fermentation. And we have spent recent years trying to untangle the system, characterize it. And through there, we use that knowledge to develop our starter culture design. And so we do carry out multi-species fermentations, but we're in the process of establishing this research. It's really much more to look at. Yeah.
Thank you. This one is around, I think more like your experience and your opinion. So would you say that there's a lack of fermentation capacity for food applications today as compared to higher value biopharma products application?
I would say yes. Over here in Singapore and around the world, there are, it's quite easy to find biopharmaceutical factories which are already using standard bioreactors to produce pharmaceuticals. In food industry, we really only see non-precision fermentations. So what I'm talking about is, yeah, you can produce yogurt, just put it in a tub and let it go. There's no control at all. And when nowadays, when a lot of startups are moving into this area to do precision fermentation to produce various improved food ingredients, for example, they do find that there is a lack of facilities, researchers, and all the related support. And as a result, we do have a long queue outside our door.
Yes, so I think the next question will be on the yields. What are the best yields that precision fermentation process generates in your experiment and your experience?
The best yield. I'm not sure how to usefully answer this question. We usually look at the amount of, let's say, the sugar that we add in, and then there's a theoretical yield for the biological system. For example, how much biomass would be expected from glucose. And so, for example, for the E. coli system, glucose mainly goes to biomass and acetic acid and carbon dioxide and the rest. So we are able to control the bioreactor to get just biomass. So that's like a full theoretical yield. But at non-ideal times and conditions, you would even get no biomass. So zero biomass yield and all being converted to acetic acid instead.
Thank you. Yes, I do have one question. So with the parameters in your last section on the scale up, with the parameters you start looking into right now, do you think when we know how those fluctuate in parameters impact on the microbial growth or microbial production, will we be able to design and engineer a better bioprocess for different target molecules or different microbiomass from those information and from those parameters that you've studied?
I would say the first approach I would reach for is to go and improve the strain. So this characterization exercise could tell us that the performance of this strain is going to drop, say, 50% under fluctuating conditions. Then I'll feedback this to the guys who developed the strain and say, can you make it more robust? It seems to be not too sensitive to oxygen. Yeah, so that would be an approach which hopefully produces a better strain. Of course, other ways of strain improvements such as strain evolution and all that can be utilized. But I'm not sure how much we can do about the bioreactor itself to reduce fluctuation, because practically speaking, it's just a standard large-scale bioreactor that you find in the market right now.
Right. So do you think there will be an initiative to work on the hardware itself to actually improve this, or we will actually need more demand coming in on this for such improvement to be interested for bioreactor provider to start looking into something like that?
Well, definitely. I'm just thinking that over the last decades, there was not much change in the bioreactor design, the vessel at least. It's a very nice, a perfect cylinder with as much mixing as you can, and that's, I think, I don't know what the engineering limits are. Of course, impeller design is definitely something that we should look at, and we are looking at, that would help in improving the mixing. Yeah, I have heard of different ways of sparging in air, adding in substrate, but they seem to have been met with resistance from operators and practical parties. Yeah.
So I think we have time for one last question. Other than homogeneous oxidation, are there any other significant challenges in the production process to make precision fermentation at scale that will aspiring manufacturers need to consider? So
if we talk about economics, that means you want to have good production. That would also relate to many factors. How good is your strain, and also how good your process design is, and not forgetting the raw material cost. So what are we feeding to the cells? Many things can be optimized. Yeah.
Okay. I think that's about time for us. Thank you so much, Professor Chow. I've learned a lot myself today, and we are excited that we start seeing more fermentation activities in the region. And we hope that we're going to stay in touch, and we'll learn more about any other works that you're working on, so we can share that more with our community. For today, thank you so much for your time and your knowledge and your expertise. Thank you everyone for attending. Hope you guys have a good experience and learned a lot as I do. So with that, I would like to wrap up this session. Have a great day, everyone.
Thank you.
Thank you. Bye-bye.